All right, so typically the lecture to begin with, I'll just talk about some announcement, something I want to remind you about. But typically you'll get announcement from E-class anyway in the written form. But for today, so from Monday, we already finished going over the official policy in the syllabus and also the open letter. Let me show you just one more time, okay? But please make sure you read through everything and make sure you're clear about the expectation, right? I think that's the most important thing for you to succeed in this course. If you go to the lecture site, you will see that syllabus is right here. I don't think there will be any changes really, but if there's any, until maybe up to 2 weeks later, I'll definitely let you know, but I don't think so. And then the open letter, okay, we went through some critical parts, but please read through the rest as well, okay? And then I may not bug you really every time when I post like a new slides or maybe new iPad notes. So please always check over here. For example, for today, you can see, click on the file. The template I'm gonna go over will be right here. All right, so guys, please just always check. I would say to be safe about 1 or 2 hours before the class, then I will definitely give you the latest version. Okay, and then tutorial. Right, your tutorial number 1 will be tomorrow, 2:30, SLHF, I believe, right? So please be there. I'll be there, greeting you to actually talk about some fun stuff. And 2D arrays, that's what we'll talk about. If you have already learned it, maybe back in the first year, great. It's just good to review, just to review the relevant part, actually, for the use of this course. Why would that be useful? 2 things, okay? So 2D arrays. So one is, when we later on talk about graphs, the graph ADT, you have to know, well, we're gonna learn about theories, algorithm, proof, etc. But it will be also very useful for you to know how to implement graph as well. One of the implementation strategy for graph, which is rather efficient, is called adjacency matrix. I'll just mention the name right now, right? So one is about adjacency matrix. And of course, the matrix right here refers to 2D array. I'm going to show you using the primitive array mostly for tomorrow. So that will be the most intuitive one to get started with. But I'll give you maybe some option as well. You don't really have to use, let's say, array of array. You can use array list of array list as well. That's going to be equally functional for 2D array, right? So adjacency matrix is definitely one important part you have to know. You may even have to program a little bit about 2D array in the programming test, but I'll confirm. You don't need to worry, right? I'll make sure you're prepared. And the second use will be, in maybe the second last week or maybe the last week, we're going to cover a bit about something called dynamic programming, in which case you also have to use 2D array. And of course, once you design the algorithm using dynamic programming methodology, you have to know how to put it into practice as well, right? Into working. Dynamic programming. However, for tomorrow, I'm not going to touch upon these two. It will be too premature for you to learn that, not just yet. So tomorrow, I'm just going to start you from scratch, walk through the basic syntax, and also about what will be the advantage of using 2D array over 1D array, and also do some exercises together, right? It's going to be very interactive. Just bring your laptop, please, okay? You can just follow along with me. Well, if you just want to watch me doing it, that's okay. I'm going to record the session anyway, and I'll take attendance, trial for tomorrow. But later on, we'll do the real thing, okay? Any question about the course so far? Any question you want me to clarify? All good? Okay. So today, I think at least for the very first half, I just want to talk a little bit more about, number one, to clarify some terms for this course, and especially the engineering section. We have to know why this course, how this course can be fit into engineering. Just one slide, just to get your attention very quickly. And then I will talk about some motivating problems. At least 2 or 3, just to give you some idea about the problems that you should be capable of solving at least, right? Of course, you can be creative about solving something similar beyond this course. We'll talk about them as well. And some of them will be related to your 2101, so that'll be a nice review as well. And in the second half, or maybe this last 1/3 for today's lecture, we'll start reviewing about asymptotic upper bound, big O, really. So the slides are really there. It's really self-contained, almost like a textbook in some way, right? Like a concise textbook. I'm going to assign some slides for you guys to read over the weekend. I'll choose some of them to really talk about, in the lecture, and then we're going to work on the more advanced example maybe next Monday when we resume. Okay. Good. If you have no further questions, usually I also try to recap what we said earlier in the lecture, but nothing really technical said on Monday, so we don't have to. But today, I'll go directly to the point. So one slide you will see on the administrative issues slide. I think slide number 11. Okay, this slide here just set the context. You know, there's something I try to present in 2030, 2101, 3101 engineering section. For those of you who may want to be licensed a professional engineer, it might be part of the job requirements. So this course is actually really designed along that spirit, right? You can definitely read the slides, something called Code of Ethics, which is about expectation on you being a professional engineer. And there are many aspects over there. I'll just mention 2 of them, all right? You can definitely take a look. Knowledge and competence. Right? These 2 are definitely something we're going to focus. We're going to focus on theoretical knowledge about algorithm, learn about how you can analyze the running time and correctness, and also about competence. How can you put things into working implementation? Just on paper and pen is not sufficient, at least for the engineering discipline. Maybe for certain area for theoretical computer science, you don't necessarily have to code. You just write pseudocode. But we don't really do that in this section here. We really want you to put something into working that's going to be more useful for your future career. All right? And in real life, of course, if you're an engineer, you have to be responsible for the products you actually build. In case there's anything that's kind of fails, you may have consequences, maybe financial consequences, or maybe even life consequences. If you're lucky, only get suspended for your license. Otherwise, you might get a lawsuit. All right? Anyway, this slide here, just for you to keep in mind, right? You really want to have the rigor when you actually educating yourself towards engineering degree or license. And for Ontario, there's some association called PEO. And if you are interested in doing that, you can look into it. But if you want to relocate yourself to other provinces in Canada, the same rule. Okay, anyway, just for your information. Okay, good. And then I want to go back very quickly to the course learning outcomes right here. Okay. And you will see that some of the course learning outcomes is actually consistent with the prerequisite, like a 2101. So you actually want to choose the appropriate algorithm. There might be actually alternative, maybe data structure or algorithm you can choose to solve a problem. You want to see which one is the more efficient one. Okay? That's something we'll see. Okay? For example, let's say even for sorting, which algorithm should you choose? Maybe you want to choose a heap sort or merge sort. But if you do choose a quick sort, like what we said last time, you got to make sure the pivot was chosen properly, right? Okay, and also you ought to know how to design a new algorithm. Maybe for in this context, for example, in the exam, or maybe in the test, I would say, maybe I will give you a slightly different problem than what we solved in the class. How can you design something similar, or maybe like a slight extension to it, right? That's the minimum you can expect, really. And we're definitely gonna do a little bit of recursion, not the emphasis, but for sure greedy algorithm as we dive deeper into the graph theory a little bit later. All right, and we'll talk about proving correctness using mathematical induction. I'll give you guys a mini lecture on mathematical induction and with many examples. We'll do that maybe slightly later after we review the big O and also do something about the trees to review. Okay. And proving the bounds, we're going to focus on big O, which we'll start today, and also the standard graph algorithm. Okay? And for this one here, I just want to mention 2 terms, which you may have heard about before. Typically, think about this, 2101 question. Let's say you're given a tree. Let's say binary tree, make it easy. What are the possible ways you can systematically traverse every node in the tree? How many ways are there? Binary tree. 3. Give me the 3.
In order, post order, and then
pre-order. Yeah, pre-order, in order, post order. All right, very good. I'll write it down. This might be something nice to really put as a comparison right away. Okay. Whenever you talk about trees, let's now say binary trees, because as you guys know, for in order traversal, it only applies to binary trees. Right? That's from 2101. So for trees traversal, we got pre-order, in order, and also post-order. We will run into, especially, these 2 at some point to make some comparison to graph. So we don't need to review at this point. And then for graph, luckily, only two. Traversal mechanism, okay, systematic. And that one there, I'll mention that. You may have heard about them before, okay, for graph. It's called depth first search. And also breadth first search. Either depending on the, based on the depth or the breadth, right? Exactly what I really mean, we'll leave until we get to the lecture, a little bit later, okay? And the standard acronym will be DFS and also BFS. So this learning outcome here actually says about two things over here, which is quite important for you to also keep in mind. The standard traversal algorithm for graph will be either DFS or BFS. And then if you want to devise some new algorithm for yourself on your own graph application, most likely the new algorithm is going to be based on either DFS or BFS. So there will be many graph questions, either existing or new ones, that can just be solved using these two. That's something I'll show you as well. There's simply a series of basic questions you can ask from the graph using DFS or BFS. That's something we'll see as well. For example, topological sort, which we briefly talked about last time, it's a graph algorithm. That one is simply based on a few lines of extension of DFS, for example. Okay, we'll see that one as well. Okay, that's about cross-learning outcome, but we'll definitely cover bit by bit as we go. Okay, I want to talk about some motivating problem, right? So maybe for the next maybe 20 to 30 minutes, that'll be nice to actually mention about the terms and also things you have to, you can look forward to, throughout the term. The first one. So this slide here, just about data structure algorithm analysis, that's more like a repetition from what you will see in the asymptotic analysis lecture. So this one here, I'll skip it just for now, but I'll talk about it a little bit later. All right, here, a searching problem. I'll take this one, it's more like a review motivating problem for 2101, just to a little bit check if you still remember certain details quickly, all right? So let's say the problem is we have a mega city. It could be Beijing, Shanghai, London, Paris, or even Toronto, right? We got many people in the city. Let's say we got 10 million residents. And 10 million is simply 10 to the power of 7, right? And let's say we want to store every citizen's record in some database. And now the question is, what should be the data structure of the database, right? It could be an array, which has 10 million slots, or it could be a tree with maybe 10 million nodes, right? And now we want to figure out, okay? Let's do something very, very quickly, just to visualize what the problem is, okay? If you took maybe 2101 from me before, it's the same motivating problem. But for this one here, we don't do everything from scratch. I just want to use that and mention some facts very quickly. Okay. So let's say the naive solution. You have a database which has a single array. You can think about array list, linked list, doesn't matter. Just a linear collection. Okay. So here you got some index from 0 all the way to 10 to the power of 7 minus 1, right? And if you choose any arbitrary index in the array, it's an index. And then, assuming that everything has been, every slot has been occupied, let's say. And then, over here, we have some objects of type resident record. Okay, so let's put resident record right here. And then, one of the attributes is called SIN number. So let's say, assuming that every citizen has a SIN number, well, kind of like an ID that's kind of unique, like a student number for you guys, right? Or employee number for myself, okay? So that one there would be an attribute called SIN. And it's simply an integer value over here. So when you search for that, it's going to be a very straightforward linear search that is simply just go from maybe from left to right, right from left, doesn't matter. And then when you look at a particular record, compare its SIN number against the input parameter, arguments. If they match, return it. Otherwise, keep searching. All right? Quick check. Is this the most efficient solution you would know about? In 2101, most likely, yes. But what about in this level, 3101? Did you learn anything from 2101 that's going to do maybe better than an array? Let's start with the array. Oh, sorry, just before I take your answer, okay? Let's say for the array, how bad is it? If I want to search, let's say I want to execute for this code over here, just go left to right, let's say. What's the maximum number of iterations I may have to run? 10 million, right? Exactly corresponding to the size, right? That one. I should really make it rhetorical. I shouldn't bother you. That's straightforward. So worst case should be big O of n. And n will be the size of the database. It doesn't need to be like exactly the last element you have to reach, as long as it could be n minus 1, could be n divided by 2, right? You will know that lower term can be dropped, right? That's something we'll review as well, mathematically. That's pretty good. We don't need to worry too much. So now, that's not efficient. I want you guys to tell me, based on what you learned from 2101, what will be the efficient solution? Go ahead, please.
Is the array already sorted?
Oh, okay, good question here. Let's say array is not sorted. Let's say this. The input you're given could be an array or something else. Let's say if you say array input, just say unsorted. Oh, just before, actually reminded me something. Before you guys tell me what exactly you think that might be the most efficient one, let's consider a candidate solution, okay? A candidate solution. You guys are going to tell me whether it's good or not. So think about typically when you want to make a decision about which data structure to choose or which algorithm to choose, there are two possible input you might be given. You might be given, like what I'm going to tell you, like a little more like a pseudocode, like a natural language description. Or you might be given Java code. So either way, right? So both you should feel comfortable. Let's say this one here, I'm basically given some input array, let's say. It's an array which may or may not be sorted. Sorted or unsorted. I just cannot make that assumption, all right? Sorted or unsorted. And I simply want to search for that SIN card, right, a SIN number, okay? And aside. Do you guys remember binary search, right? If I want to perform binary search on an array, do I have any precondition that must be met? Or I can do binary search on any arbitrary array?
The array has to be sorted.
Has to be sorted, right? So now let's say in this solution here, I want to do binary search on the array, meaning that before I can do it, I have to make sure binary search is applied in the right context. I got to sort the array first. So what I will do is, step number 1. I am going to sort the array. And as we reviewed last time, the most efficient way possible, let's say merge sort and log n. Of course, if you go for selection sort, insertion sort, that'll be n squared, right? So let's say n log n. And after step number 1, the array is sorted. Now, awesome. We can apply binary search, which we know is efficient than linear search. Perform binary search. And that one there we know is going to be big O of log n. All right, so that's kind of, think about in the, let's say, exam, right? If I give you, I might only give you about candidate solution and only step 1 and step 2. These two things are something you're supposed to derive yourself, right? I may not give that to you, okay? Now, based on what we know so far, is this candidate solution the best possible? Let's answer this question first before we follow up. Go ahead. No, how come?
The other one only took O and
The other one only take?
O and
Oh, big O of n? You mean linear search, right? Okay, that's good. Why is this one bad? What will be the running time? And log n. Because this algorithm over here is not only about step number 2. Step number 2, yes, is efficient. But the problem is step number 1 is going to dominate, which would be n log n. Right? You see my point? Whenever you want to consider your algorithm, there will be multiple steps involved. You want to find out the step that's gonna dominate the running time. That'll be the running time for the algorithm. Just remember. In some way, this one tricky, right? You might think, oh, I'm doing binary search. It should be efficient. Not really. It turns out it's actually even worse than linear search. Think about these two. Overall, it's going to be O of n log n to do a search. In fact, it's worse than a linear search. Okay? That's good. Okay, now the question is, how can we do better? We want to do better. Definitely, we can do better than n log n. We can simply do a linear search, which is big O of n. Can we do even better? Anyone? Yes? You can use a hash map, okay. Hash table is something that we wouldn't really cover. Hash table, hash map. It's not something we'll cover in this course, but I can just mention something very quickly. Hash table, yes, in the best case, it will be almost like a constant because you can use the number as an index. But you may have collision. In that case, you might still get as bad as like a linear. Okay, yeah. Dictionary, okay. Dictionary, I like it. Dictionary is like an ADT, right? But now, what's the data structure you're talking about? Huh? Not hash map. So hash map, again, we wouldn't really go into it, but for those of you who might be interested, this one here, you might suffer from something called collision. Okay, we wouldn't go too deep into it. That one will still be big O of n. Okay. But dictionary is something I would like to hear. To really implement dictionary, we need a binary search tree. All right? So now the question for you guys, okay, I'll go a little bit further. Right here, all right? If I say a BST, is this going to give me the best performance possible for a search? So at this point, you want to think to yourself, what's going to be the performance bottleneck for a binary search? Sorry, a binary search. What's going to be the performance bottleneck on the binary search tree? And let me remind you very quickly, okay, before I take your answer, right? Let's visualize it, right? Let's say we have a binary search tree right here. Okay, we wouldn't go too deep into it. That's something I will review as well when we get to the tree rotation later. So you start with the root right here. And the search path is going to be something like this. I might go to the left, go to the right, go to the left, go to the right, go to the left, go to the right. In the worst case, I may have to go from the root all the way down to some leaf or the bottom of the tree. Agree? All right, conceptually. So now, what would be the running time for a search on a binary search tree? To really express this accurately, a hint for you, you may not want to use the number of nodes as n. You may want to use another measure of the tree. I'll take the answer first.
The height of the tree, or I think it's log n.
Ah, that's good. You actually said exactly right, okay? It should be the height of the tree, all right? So whenever you want to do a search on a binary search tree, you got to start from the root and go all the way to, in the worst case, the bottom of the tree. So that means the running time is going to be proportional to the height of the tree. All right, that's good, okay? That's exactly right from your fellow students. Big O of h. And h is the height. So this is the most accurate way to represent the running time for a search on a binary search tree. Now, look at the h, right? That's something I may need to review as well. There will be certain mathematical property you have to know for binary tree or tree in general, okay? So now, if you're given the height being h, what will be the relationship between h and n? So now I got h over here, and then what about n? Right? So this way, you want to think about, given h, what will be the minimum value for h in terms of n? And also, what will be the maximum value for h in terms of n? Go ahead.
Minimum would be log n, maximum would be n.
Yeah, yeah.
It's just a line.
Yes, I agree. Okay. So guys, if you really kind of roughly recall what I'm talking about, that's a good sign. We're going to review details about these, right? I want to just give you some high-level detail. All right, so now for big O of h, right? The best case is going to be big O of log n. The worst case is going to be big O of n. What does this mean? This means if I tell you that I can build a binary search tree for you for the database. However, the worst case for search can still be big O of n, because the heights may not be as balanced as we might hope that would be. All right? So if you look at the best case right here will indicate the tree is balanced. So our original question, I'll get to you. Our original question about, is binary search tree sufficient for efficient searching? No. You're missing one keyword, balanced. All right? It should be a balanced binary search tree. All right? That's something we got to review as well. Okay, one more thing, and then we can move on to another motivating problem. So for balanced binary search tree, I will only assume that maybe in your 2101, either your instructor, either myself, or maybe other colleague, they might only talk about how you can determine if a tree is balanced. How you fix the balance, I assume you haven't known about it just yet. We're going to cover the two ways for you to maintain the balance for the binary search tree, for the binary tree. So this is something we're going to see after we review the asymptotic analysis. It's called the self-balancing. Binary tree. Okay? And this way, it can somehow guarantee we can actually get some very minimum heights. Okay? And to really achieve that, there will be two we're going to look at. Okay? So one is about, it's called AVL tree, but it's really about doing tree rotations. That's something we'll see first. And the second one is called heap, which we also mentioned earlier. But heap is not really for general search. It's only for searching the minimum or maximum. I just categorize that as also a search. Okay? Anyway, that's something more or less you will have learned already in 2101, but we're going to review that, right? Just to make sure we can connect to the context for this course. Okay. Any questions? Anything you want me to clarify? Okay, good. Next one. Okay, compiler. Okay, you guys learned about trees in 2101. If you also know about roughly how to code about trees in Java, you're really ready to build a compiler. Okay, compiler is actually a very important technology or skill to really learn, because compiler can simply transform one thing into another. So there's a course called EECS3101, but it's only usually for CS student. For software engineering, I guess you have no scope to fit it in, but that's okay, right? I just want to point it out. It's definitely very, very relevant to algorithm, okay? So compilation is really a transformation from one thing into another. The example I'll give to you is something like you can go from Java into SQL database, or you can go from C code into what you learned in 2021, machine instructions, for example, right? So that's just two possible examples. So let's just take a quick look, okay? This is the very conventional use of a compiler, okay? Just take a quick look, okay? You may have seen this example before, but for those of you who haven't, let's take a look. Let's say this is some language that I designed myself, like a programming language. Across over here, simply like a way to expressing loops, pretty much like a for loop. I have three variables, B, C, and A. Okay? And then I have some dummy variable, like a loop counter I, which is going to loop from 1 all the way to n, and n may be the size of certain things, right? Let's say n is also declared somewhere. In the body of the loop, for each iteration, I'm going to read some external input and store that into D. And then all I want to do is I want to update the value of A by this expression right here. All right? A very conventional use of a compiler is to take one programming language and rewrite it into another construct using the same language. But somehow, the performance will be optimized. That's a very typical use. But to really use a compiler, that's only one possibility. You can be very creative about how you build a compiler, but that's beyond the scope for this course. Guys, very quickly, how do you think we can improve the performance right here? Any suggestion? I can tell you that may not be something here. I don't think you can save any time right there. Diego.
Could you possibly combine the repeats that the A assignment step and then maybe build one line so that A gets assigned the same operation, but then instead of having an extra step to repeat, you just wait it on the spot?
Yeah, pretty much on the right track, yes. Yeah, let me just make it a little bit more explicit. If you guys look at this particular variable assignment, it's going to be done for n times. So we want to make sure each time is as efficient as possible, right? So especially if you look at this part of the expression here, 2 times b times c. Okay? First of all, you can see a here may change between iterations, right? Because a is updated each time. D here also may change between iterations because D here is also going to be dependent on the user that's going to type from the keyboard standard input, right? So about 2 times b times c should always be the same value. If you try to evaluate this expression every time you want to execute it, it's a waste of computing resources, right? So we say that this value over here stay invariant. Doesn't change. How about stay unchanged? That might be a little bit more intuitive. Stay unchanged between iterations. Anything that can stay unchanged, we should move it out and make sure we only evaluate it once, maybe before the iteration even started. Right? So this is one program, assuming that you have a compiler, is going to compile this and then using the same syntax into another program. We say that this program here behaviorally is the same, semantically is the same. It behaves the same way. However, you will see that we factor out this particular invariance or unchanged expression here, and we simply evaluate it only once. Evaluate it only once. And then you can use it for as many times as you like. So rather than computing it, you can just access the corresponding memory and get it. Right? So that's one optimization, right? A very minimal example just for you to see the idea. A compiler is simply going to code up many different rules depending on the pattern you can recognize and then do the optimization, right? But behind the scene, what's really the trick, right? Somehow, the compiler will be able to parse. Yeah. For those of you who are in software engineering, I know you haven't really learned about a concept like a context-free grammar, deterministic finite automata, but that's okay, right? I just wanted to talk about a general idea. If you happen to be from CS, I think EECS3101 is really the background for this kind of knowledge, but that's okay. It's only for reference. So the parse over here is going to somehow turn ASCII characters, like a file or whatever text you have, into a tree. And this is something called abstract syntax tree. And as far as you're concerned, let's say from 2101, it's a general tree. It's not necessarily binary. It's a general tree. Okay? And this parsing is automatic. It's actually by some compiler tool. And for those of you who might be interested, a tool that's very industrial standard is called Antler 4, and they support many languages for your compiler construction. Doesn't need to be Java, it can be Python. I believe they support maybe C# or C++ as well, but I can look into it. Antler just one example, okay? Okay, for those of you who might be interested. And the tutorial link I included in the lecture slide is actually talk about Antler 4. So at this level here, you guys are ready to learn about compiler. Not required for this course, but I think it will be a nice addition to your skill set, okay? One more thing. So once you have got this tree here corresponding to the original program, so now you can do as many transformations as you like. So this corresponds to the kind of traversal, maybe variable assignment, whatever programming tricks you have to do to transform from one tree into another. Of course, in order to implement a compiler well, you have to know recursion very, very well. But that doesn't really mean if you're not good at recursion just yet, you shouldn't touch a compiler. No. If you want to be good at compiler, you should really try, if you want to be good in recursion, you should really try compiler. That will be the way to perceive it, all right? So the transformation here is basically just about recursion, mostly. Recursions on trees. Okay, I don't want to touch too much about it. It's more about just some general reference. Okay, anything you want me to say more about compiler? Is this going to be on your programming test? No. All right, if that's something you want to ask me, definitely not. All right, but it'll be very nice if you can spend some extra time. You know, that's very nice to actually learn about it. Okay, so now let's talk about. I think I got 1, 2, and 3. Okay, 3. Let's talk about 3 motivating problems very quickly on the graph. So this is a graph. Okay, first of all, what is a graph? Okay, let me talk about some very general concept first, and we'll take a short break, and then we're going to resume and finish the other one. The other one wouldn't take long. Okay, just give me one moment. There we go. Okay, let's now do a very quick clarification. So we talk about tree, and also we talk about graph. Tree, you learned from 2101, something like this. Right? It's a binary tree, right? Right, just a tree, right? And graph is like an extension to tree. Extension to tree by allowing something called cycles. I'll visualize it, but I'm going to define cycles a little bit more formally later when we get there. Okay? So let's say I still got something like this, right? However, I might also allow this one to come back here and this one to come back here. That's allowed. So graph is the most general way you can represent the relationship between different objects or different entities in your application. So most likely, you will have to use a graph for your future application, not necessarily trees. Okay? So to put it a little bit more formal, you know, implication, right? So we can say that a tree is definitely a graph. However, a graph, not necessarily a tree. Not necessarily. Because a graph may contain a cycle, in which case it's not a tree. Okay? Okay, a very quick distinction. Because there might be cycles. Okay, if you like another diagram here, I can put it right here. Think about tree. Let's say these are all the possible trees. It's more like a set right here. And the graph is much more general. It's going to be many more possibilities you can imagine. So that one there would be graph, okay, right here. So think about graph right here. Okay, and of course, every tree has no cycle. And then if you think about anything that's a graph but not a tree, it is a graph, but it's not a tree. That means it contains a cycle, right? As easy as that, right? Because cycles. Yeah, so this diagram here really just corresponds to the implication I'm trying to formulate here, right? It's very important to make such distinction, minimum, all right? Okay, I would suggest that we take a very brief break. And also, we'll try the iClicker very quickly today as well. And then after the break, we'll finish off the motivating example. Okay. All right. So before the break, we basically just talk about between tree and graph. The main difference is about having cycles, right? Just something to keep in mind. But it's something we'll definitely elaborate a lot more once we get to the graph lecture. But let's see 3 different problems that you will actually see how to solve when we get to the graph lecture later. Okay. The first one here is so-called, even before I get to the problem, right? Let's now convince ourselves it's more like a graph. So this is more like a like a flight map for some maybe airline company. For example, you will see that maybe there's one airport from Miami, maybe one from Boston, and one from New York, etc. Right? Of course, it's like a simplified one. A realistic, maybe a flight map would be much more with many more cities and many more routes. Okay? And just very quickly, right? For graph, the most critical two components there is something here for each, for example, city over here is called a vertex. Right? And also between every between every two vertices or between every two cities. Okay, let's say over here. That one is called an edge. Okay, so that's some term you will actually run into very often. So that's why if you want to program, let's say implement graph in Java, you want to have one class for vertex or one class for edge. Okay, but we wouldn't get into detail, right? So now, what is really the shortest path problem over here, right? Let's say, for example, let's say I live in Boston. There's no Toronto here in this particular map. So let's say Boston. Let's say I live in Boston, and I want to get to San Francisco, right here. And you will also see, not necessarily for all the map, not all the graph, for this particular graph, there's another very important thing. For every edge, there is some numerical value, right? Let me use a different color. So this is set to be the weights for the edge. So we say it's a weight of a particular edge. It's not a weight for the graph. It's on the edge level, all right? So when I say to fly from Boston to Miami, so 1258 represent the distance, right? And if I want to go from Boston to, I'm not sure what this is, and then go from there to here, right? That's going to involve these two weights. If you add them up together, that'll be the total distance, right? Etc. So now, the shortest path problem, very intuitive. If I want to go from Boston to San Francisco, I want to find a path. There are many paths, for example, right? Let me just give you two examples. I can either to fly from Boston directly to San Francisco. Okay, this will be one way. Or I can try to go to JFK, and then I can go to Miami, and then I can go to LA, I think, and then San Francisco. That's another possible path, right? There are many different paths between two vertices. Now, shortest path tells me I can find a path whose summation of the weights or the distances will be the minimum. All right, I'll write it down, okay? This is a problem you will find relatively straightforward or routine to solve because we're going to learn about some algorithm to solve that, okay? So shortest path, right here. So it's going to be a path whose summation of edge weights is the minimum. And we're going to learn an algorithm called Dijkstra algorithm. I'll also write down the name. That's something we're going to dive very deeply into. It's a conceptual idea about Java code, pseudocode a little bit, and also about writing time, and also about mathematical inductive proof. Right? That's something we're going to dive very deep into a little bit later. Okay. So we're going to learn about Dijkstra algorithm. Okay, Dijkstra. Just mention the name. Okay, that's one problem. Okay. The second problem over here is something called minimum spanning tree. Again, we're given a graph. Okay. So it could be that I don't necessarily only want to travel from one city into another. Let's say this particular input is all the cities I would love to travel. Ultimately, I would like to cover every city in this particular map. Now the question is, what would be the cheapest way in the sense that I can travel the minimum amount of distances to cover all the cities? Okay, I'll write it down. minimum spanning trees. Of course, we got to make sure we define that properly, which will take some time later. In this particular example, I want to travel, or you can think about cover. I want to cover all the cities. All cities or the vertices in the map, which is indeed a graph. Okay? Well, I wouldn't dive very much into it, but let's say this. Given this particular input, right, the algorithm we're going to learn about is going to tell you that somehow this will be the minimum. Okay? Which means you may just want to go starting from Boston, and then I can go here, go back, etc. Right? So just use a way to cover all the cities in the graph from the minimum summation of the distances. Right? Just gives out intuition. Right? Just another way to really play with the graph. Okay, last one. This one here is a little bit more like a contrived example here, but I can also tell you can immediately imagine. Imagine every vertex or every node here could be, first of all, it's something called topological sort. Sort is not in the sense about merge sort or quick sort, not really. You're not really giving an array and then sort it in from smallest to largest, not really. Given a graph, you want to give a sequence. Topological sort. Okay, just bear with me. Topological sort, I just want to talk about a very general idea, but we'll get to it also later once we talk about the depth first search. Okay, there we go. Okay. Topological sort is something, let me not pollute the diagram. So given a graph, you want to produce a linear sequence. Okay, I'll say for example. Let's see how do we interpret this graph over here. So here it is saying that before I go to work, I want to make sure I exercise and I have breakfast. Which means exercise must come before go to work. Breakfast must come before go to work as well. Similarly, before I have lunch, I have to make sure I teach this particular course. Let's say 3101, right? I should have changed the name, right? Before I go for lunch, I must make sure I teach this course, and I have to make sure I have my coffee. It's not acceptable if I try to have my coffee after I have lunch, somehow. So this particular graph here is something called, I'll mention the name, DAG, Directed Acyclic Graph. And this graph here basically boils down into dependencies among different entities. Something must be done before something else. You want to encode all such rules, all such constraints in the graph. And then you want to go from there, generate different possible order. I'll give you an example, just one moment. It's all about dependencies. Can you imagine another very relevant example to you guys for your degree? Yeah? Prerequisite, right? For example, right? Let's say 3101, before you take it, you must make sure you complete 2101 and possibly got to complete other requirement courses as well. That's called prerequisite. And you can check email and do exercise, doesn't matter which order, right? Etc. Right? Okay, just give you a little bit more feel. Just one. According to this particular diagram here, okay, let's say I have a particular sequence I would like to live my day. And I'm just gonna use ABCD, right? Let's say I want to check the email to begin my day, and then I want to have my breakfast, etc., right? B, and then C, and then A, and then D, and then F, and then E, and then G, and then H, and then I, and then K. Let me double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We got exactly 11 vertices in this graph. All right? So now, I just want you to know two things from you. Number one, is this particular sequence here legal with respect to the graph I have? Question one. Question two, if that's not legal, tell me some violation. This is something we can do very intuitively right now, but it's something you have to do automatically using algorithm later. Yeah, that's one example. Yes, okay, I'll just. Yeah, so for example, you can see that here we say C followed by A. However, if you look at that, constraint tells you that A must come before C, right? That's the rule. But somehow you just got it wrong, right? And for your information, there's another thing that's violated here as well. Because over here we say that E must come before F as well. But here we got FE. Right? So the topological sort is actually also a very practical algorithm for you to solve different problems in different contexts. I'll mention maybe something a little bit different, also completely different to you, more like in a program analysis point of view, right? I will do that later, right? But just for you to get some feel. Any questions? Okay, okay. All right, so I think that that's all about the motivation about some problems that you can solve by completing this course. I try to put a little bit more emphasis on the graph algorithm, like a graphs, because that's definitely something new that you haven't learned from 2101. Okay. So what we should do now is to review some stuff. Okay. All right, so this slide is done. So that's asymptotic analysis of algorithm, right? The slides is already on the slide. I would suggest try not to really print it out just yet, if that's your plan, because I might still make some minor revision, maybe over the weekend, or maybe before we finish the lecture. I would say always try to only print out the slides maybe after a whole lecture series is actually finished, because I do know you guys got some print quota for your student account, so don't waste it, right? Okay, so let's just go over something here, and then today we might just go over some very preliminary stuff I want to go over, and then I'm just hoping to at least, hopefully we can finish all the big goal, definition, property, etc. in just one lecture, and then we can move on, okay? And do case studies. Okay. Let's see here. This slide here, just to remind you guys, right? This course, there will be a programming components, which means you have to make sure you can write Java. I'm pretty sure you can write Java. But I got to make sure you can write Java in a way that you can pass JUnit test cases, right? That's something you want to make sure you know. And also how to use debugger, right? I do have references for you. But if you're not too sure which part you should really revisit, you can speak to me. I do have my office hour today, right? Today and tomorrow, 4:30. Okay, so we're gonna just very quickly distinguish between algorithm, data structure, and also how we measure how good the algorithm is, the efficiency, and etc. Asymptotic analysis, and then also right here. Okay, all these will be more like a review about what you already learned from 2101. So I'm gonna tell you the slide range. That'll be some assigned reading for you guys to learn, right? To maybe go over over the weekend. I'm not gonna talk about all the slides. I'm just gonna select some of them. I'll talk about some of them today, and some of them maybe on Monday. Not a tutorial. Tutorial, we should only do exercises, right? It's not like another lecture time. You shouldn't be, right? Just do exercises. But we're gonna also look at two case studies. I'm pretty sure you have seen that maybe before, selection sort, insertion sort. We can briefly take a look at some working implementation for these two, and then we can see how we can figure out its big O, running time. We can take a look, right? And the challenging part at the end, which I hope to get to maybe on Thursday beginning, right? Sorry, not Thursday, keep getting confused. Wednesday, I meant that. So here we're going to talk about dynamic arrays and also average time analysis. I'll do one example in the lecture, and then we can do the more challenging one partially in the tutorial. Okay, so that's what we'll do. Today, something basic. Okay. Okay. Just before that, let me just give you guys some very quick notes, but you can note down as well. Okay, right here. Okay, before we get there. Okay. So slide number 3. 17. Slide 18 will be where we start a formal definition for big O, which is something I possibly will go to, maybe not necessarily today, or maybe at least Monday, the latest. Self-study. That one there basically just try to tell you the whole story, just going from, in the most naive way, you can simply measure the algorithm running time using some time stamp. And then how we could go from there into big O, right? It just give you the whole story, right? Yeah, that's something you should really study. And of course, if you are interested about, would that be covering the test? Possible, not necessarily, but possible, right? That's my answer. Okay. All right, so let me first of all talk about slide number 4 very quickly, just to clarify some terms. Okay, right here. Okay, just about various terms. But let's now talk about it. Okay. So just link everything together about computational problems, and also data structures, and also algorithm. All right, talk about these 3. And then I'll just give you some example that's relevant to about graph as well. Okay, let's build from scratch, just about the various terms. And that's something the high-level roadmap or picture you should really have, since this 3101 will be really the course where we try to synthesize many things that we learned from before. To start with, you can think about the algorithm you have. In the most intuitive sense, think about algorithms depending on whether you're the user or the developer for the algorithm. If you're the user who's simply using the algorithm, it might just be like a method call, right? Input and output. So you have input, and also you have some output. Okay, so one example right away. Right? Remember the shortest path algorithm we just talked about, right? So the algorithm itself could be about, for example, the Dijkstra algorithm. For example, it would be, so Dijkstra's shortest path, SP for shortest path, okay? Algorithm. Could be the shortest path algorithm, could be the tree rotation algorithm, could be the minimum spanning tree algorithm, or topological sort, right? Just any algorithm. The input is, for example, a graph with weight. We call it a weighted graph. Right? If you recall from what we just said earlier, you can think about this is one example input with weights in the graph, right? Input, and the output somehow by executing or applying the Dijkstra's shortest path algorithm, it basically can tell you, given a particular starting point, let's say Boston, I can tell you the shortest path from Boston to every other city. Okay, that's something we'll see later. Okay, so this will be given a starting, what we say the source, vertex or the city, right? Vertex. Return the shortest path to all other vertices. It's a little bit vague, not exactly clear, but it's okay. You know, just get some big picture just for now, right? We definitely have to dive into the exact details, which will take some time. Okay. All right, that's from, and the algorithm, of course, every time you are designing an algorithm, always think about what's the purpose, what's the expectation for that, right? There should be some corresponding computational problem, right? So always think about the algorithm is really serving for some problem you're given. You don't really design some algorithm out of nowhere, right? All right, let's now put it into context, okay? So what we have is right here. There is some computational problem. Computational problem. And here, very important, the minimum you should really know about input and output. what's the input graph and what's the output graph, right? And also, if you want to do, let's say, a binary search, input may be a sorted array, and the output should be maybe some return, value, right? More importantly, that's something we'll get into as well. Whenever you specify input, it's not necessarily only about what type of input you have. If you only say it's a graph or it's an array, it may not be enough. You may want to say a little bit more about the condition under which this algorithm should be applied, right? So it's called precondition, right? That's something we'll get to as well. So either it's more like a Boolean condition for which the input you're giving to the algorithm must be true. And symmetrically, for the output, how do you judge that the output is actually right? You have to consider postcondition. Let's say postcondition a little bit like, whenever you're doing, let's say, JUnit testing, right? You try to call a method. After that, you say some assertion. I want to assert a particular value after the method call should be a certain value. That's more like a postcondition. After the updates, certain value should be the case, right? And then you can think about every time you want to talk about algorithm, it should be with respect to, it's really meant to solve. Right? And of course, the example that we're given here is about shortest path. Dijkstra algorithm is only one of the known algorithms for solving shortest path, but it's the most common one, the most well-known. I can mention some maybe reference later about other algorithms for assuming different conditions on the input. That's something we'll get to. Okay, but for now, that's fine. All right, let's now dive into, because in many cases, you will be trying to study the detail of the algorithm. So you're really more like a developer for the algorithm. So you have to not really treat the algorithm like a black box. You got to look into it like a white box, right? So you're really wearing a different hat, different role you're playing. So let's say we dive into the detail for the algorithm. So of course, there should be some step-by-step instructions. The steps could be some recursive method call. There could be some nested loop, could be some if conditional, or could be whatever, right? And then the steps is actually going to manipulate some data structure. And this is the part from your 2101, right? You learn about linked lists, array, trees, etc. Right? That will be the data structures. And this is why I want to really take the Dijkstra algorithm as an example. In order for you to implement the Dijkstra algorithm efficiently, one of the data structure you choose over here is about one critical step, which we'll see later. I'll just mention. In order to implement that efficiently, you have to use a heap for priority queue. All right, I'll just put it here for now. And we'll need to have that discussion later. So, for example, you have to use a heap for implementing a priority queue, right? PQ, priority queue. That's something you have seen before, so I'll use the acronym. Okay. All right, and then let's see what else. Okay. And of course, correctness will be the most important criteria. Correctness. Most important. Right? If it's not correct, doesn't matter how efficient it might be. Okay? Assuming that it's correct, and then we talk about efficiency. Okay? Efficiency in general can be broken down into two possible angles you can look at. You can look at the time efficiency, or you can look at the space efficiency. Okay? But in this course, we're still going to focus on like a running time. Okay? This will still be the focus for this course. Okay? But there might be, beyond this course, there might be other scenario where not only they're going to consider the running time, you have to consider how much space it's going to occupy. Especially if you're programming, for example, embedded system, the memory might be more constrained. But if you're doing other things, maybe memory is simply unlimited, right? It really depends on the context. Okay? Okay. We got about 10 minutes. I would suggest I just do one more thing over here before okay, how about just one more thing? Okay, one more thing. And then I just want to talk one more thing about from absolute running time to relative running time. You will see that as you go through the study for the slides, right? So I kind of started with a naive way to measure the running time, which is you can use maybe some system library, system class from Java to really say how much time exactly, how many seconds or how many nanoseconds does it take for algorithm to run. That's one way to do it, and then you can definitely do some measurement, but that's not the way to go, because depending on which platform, maybe you're testing your algorithm on a Mac laptop, maybe M1 model or M3, I don't know what's the latest one, or if you're using my machine here, that's back in 2014. That one must be very much slower, right? So that's something you want to see why we shouldn't really worry about the actual physical platform that we are running the algorithm. So we don't really worry about absolute time. That's something I want to clarify very quickly in about 10 minutes, and then we're good. Okay. So that's the slide you will see. You can look at the details, and then this slide here just outline about the most difficult challenges if you only use the actual running time, like a physical running time on a particular platform to measure the algorithm, right? That's something I'll let you read it and make sure you understand. And then we want to move beyond that. Okay. And maybe in 2101, you learn about how to count like a primitive operations, but we don't have to calculate precisely, right? We can just approximate about the operations, right? That's something you can also take a look. Okay, this is a slide I want to talk about before I let you go today. Okay, slide number 11. Okay, let's say this. So let's say here, so the idea goes like this. Let's say we have a value called t. Okay, t standing for time, absolute time. And t simply denotes the exact or absolute time that will be taken to execute a primitive operation in some execution environments. A little bit long, but it's more precise about what I want to say here. Right? So when I say primitive operation, you can definitely see some checklists in the slides, which is part of the assigned reading. For example, if you want to do some attribute access, if you want to do some variable assignments, or maybe some relational comparison, right? So that's considered as a primitive operation. And if you actually, let's say we got two platforms right here, okay? Let's say we got, for example, so let me just say Mac, okay? Let's say Mac M2, I believe we at least have N2. And also we got, for example, so the Mac maybe from 2014, okay? So T could be just different value, that's my point, right? Presumably, the more recent model should be smaller, right? T might just be 2. And here, T might be much larger, for example, 10, right? You can see that the number here relatively makes sense, right? The older the model is, the longer it will take for some primitive operation to execute, right? So let's now draw a table, okay? Right here. So what we have is we're going to compare two algorithm running time, solving the same problem. Right here, and also one here. So I'm going to divide that into two parts. Okay. One part, I'm going to talk about the absolute running time. Okay. The absolute running time for either the Mac M2, the newer model, or it could be the absolute running time for the older Mac. The Mac year 2014, right? That's over there, right? Compared to two. And then the column right here. That's going to be the relative running time, which is usually what you will see when you try to approximate the algorithm. Okay? That one there, let me use a different color. That's going to be relative running time. Okay? Just make it very simple. Let's say we're trying to solve the same problem. One algorithm is going to take 7n minus 2. The other one is going to take maybe 10n plus 3. And as we learned earlier, it's good review as well. N here is really about the size of the input, right? Input size. All right? And then, so these two are simply the running time of two algorithms solving the same problem. So that's why we want to compare them. If they simply solve different problems, why should we bother comparing them, right? The same computational problem. All right, let's now work out this little matrix over here, right? Let's see what we should do, okay? Let's say we assume, let's say the input size is 100, right? Make it easy, okay? 100. Let's say we assume the input size n is equal to 100. And I'm pretty sure you will, accordingly, you will be able to calculate the absolute running time in two different execution platforms, given that we know what t is. Agree? Okay, let's write it out, and then I'll make some highlights, okay? So start from this one here, okay? What about M1? We'll talk about this algorithm here on M1. It's going to be 7 times input size 100 minus 2, but to calculate absolute time, we have to look at what t is for M2, which is 2, right? Multiplied by 2. What does that mean? The relative running time here tells you about how many primitive operations do I need to involve in order to execute this algorithm. Once I know about this particular relative, multiply by what's the size of the input, and then I multiply by each execution time for the primitive operation. I'll get absolute running time, right? Let me just say one more time here. You can think about this one here is also about the number of primitive operations involved in the algorithm. All right. Let's say this. For the same algorithm, I want to see what's the absolute running time for M2 and also for this. So now, what should I fill it out right here? This part here, the relative one, should be identical. Agree? Whereas this t here is now going to be much more expensive because it's not the older model. Right? Let's write it down. So that one there is going to be also 7 times 100 minus 2, but now times 10. So you can think about, the 2 here is the t, and 10 here is the t. So now, if I just want to somehow consider this particular algorithm, do I really need to consider whether it's in this execution platform or this execution platform? Not really. You can see there's only a multiplicative constant I have to consider, and that one there can just be dropped at some point anyway. So that's why that one is not necessary. That's one point. All right? So here we talk about for the same algorithm, you really don't have to consider between different execution platforms. Let's write it down. Okay? For the same algorithm, it's unnecessary to consider. Sorry, I'm not even sure how to spell. Different platform. All right, that's one thing. Okay, one more point. Let's say we want to consider the performance difference between these two. All right? Let's say just on M2. Let's say we try to execute candidate number 1 versus candidate number 2 on the same machine model. It's a fair comparison, right? You compare in the same execution environment, operating environments. That one there is going to be, you can see the relative time is going to be different, right? It's going to be actually 10n plus 3. So 10 times 100, the input size, plus 3. And this part over here is going to be the same platform, So also multiply by 2. Okay, the second point. If I want to compare 2 different algorithms, do I really need to compare them in some particular execution platform? I really don't have to, because somehow, even if I consider a particular execution platform, this is what that will involve, T. But that can be dropped anyway at some point. Meaning that if you want to compare 2 algorithms, you don't need to worry about executing it in a particular platform. Just consider their relative running time. That's all you got to do. Okay? Okay, so that one there. When comparing 2 algorithms, there is no need for executing them. Sorry guys, I know time's up. You give me 30 seconds, right? Okay. Consider them on some platform. All right, I'll stop here, and please make sure you study these slides, and then I'll see you tomorrow in the tutorial for 2D array. Okay, bring your laptop, please, tomorrow.